Come on Monday.
Maybe I start? So, the theme is, in some sense, we're beginning the course now. In the beginning. Introduction to symplectic geometry. And Hamiltonian mechanics. So I think it's very good to have, beginning with the basic example. Confusing, this example, but I want to be very careful about it. So the manifold of interest is something we've looked at before. It's finite dimensional vector space and it's dual space. So we've looked at this before, which I regard as the cotangent bundle. Well, let me just write it in letters. The cotangent bundle of the vector space. Yeah, why not? And I will introduce on this cotangent bundle of the vector space here, the first goal is to introduce the so-called Liouville form on this cotangent, on this space. Let me perhaps emphasize it in one form in the space. And having had that one form, we will, maybe even I call it a letter that I will call it lambda later on, and this will give us actually minus d lambda, which is the canonical symplectic form. Symplectic form. So I will explain all these words. But the first thing to understand is something we could introduce very early in the course, is just a vector space plus its dual space. Some of my co-authors call this Nambu space. Nambu was a physicist who realized that looking at this thing is a good thing to do. Completely correct. I find this example confusing, so I will discuss it in a very slow way. Maybe I'll make a big picture of it over here. I only have one picture, as you know. This is the vector space here. This is the cotangent bundle of the vector space. So over a vector v, we have the cotangent bundle at that point. So this cotangent space at the vector v is identified with the dual space, of course. It's very surprising. I mean, this is incredibly, this looks ridiculously trivial. Direct sums of vector space, but it's very interesting. Okay, and very confusing. So, now first of all, let's discuss a point in this cotangent bundle. So, a point here, P. I think I will call it P. Later on, P will really have some meaning of momentum or something like this, but let's just call it a point right now, okay? I don't have many letters in mind, so this is not just a point. Okay, so P is a point in this fiber. So what that means is, it's a point P is a point V. So I purposely have P over this point V. So P is the point V plus Phi, where Phi is in V star, right? Phi is a linear form, and V, that's a point. Okay. Now the confusing thing is, let's have a tangent vector here. Okay. I'm being super pedantic because I find this confusing. Here's a tangent vector, let's call it T, at the point P. Okay, T is a tangent vector at this point. It's a tangent vector, so it's in the tangent space at P to, now it starts to get really complicated, to the cotangent bundle of V. That's where it is. There it is. But you know, if you have a vector space, the tangent space to a vector is the vector space itself, right? I mean, this is the vector space itself. You just move it all over the place. So I will write T in that way as an element of the vector space at hand. Do you understand what I'm saying? It's a tangent vector at that point. You know, this is old business in the German language. A vector has a foot point, a Fußpunkt auf Deutsch. Yeah, so here's the vector at this point. The point happens to be P. But I mean, you're thinking of this vector as just an element of the vector space, right? I mean, I think we all understand that. That's okay, right? So I've just written it very carefully as W plus Xi. Okay? So now you will tell me that I'm absolutely insane when I write lambda. Lambda is now a one form. Before I write it, lambda is a one form on the space, so the cotangent bundle of V. So this is V plus V star. This is a one form, and I'm going to write it for you now. So lambda at the point P. Right, I have to tell you what it does to T. Right? One form is applied to a tangent vector, and you get a number. Right? Well, at the point P, I have to look around here. The point P is that. The point P is V plus Phi. So what I do is apply Phi to W. Well, please look at this picture again. I have a tangent vector. Everything, there's so many identifications going on here, it's confusing actually. I find it. Again, we have a point here. This point is a vector plus a form, functional. And so at this point, I can apply this function to this vector. Right? Now I say I don't care about C. So if you don't mind, I'm going to draw, maybe a dramatic drawing here is okay. So, in this case, you're incredibly lucky because there is a vertical space, which there is always a vertical space, because it's the cotangent space at that point. That vertical space always exists. But if this is a cotangent bundle to a manifold, the horizontal space does not exist really. But here we have this horizontal direction, which is in V. So this direction, what was this thing? T. So the vertical direction is C, and the horizontal direction is W. In reality, the horizontal direction is a tangent vector down here at V. All right? So what I did is, I put in reality, this point is a one form. This point is a one form at this point, right? This point is a one form because it's in a cotangent space. This point is a one form at this point, and I push down this vector to this point and apply it. See? I push down, where did it go? Here. I took T, I pushed it down to the floor, there it is, and now I apply this one form to it. It's absolutely canonical. It's absolutely canonical. This is the Liouville one form. Okay? Now, I'm going to compute this. Yeah, Professor Schub has a remark on me.
Question. So does it live in T star V? Does this thing
Maybe I go in the wrong star. So, yes, of course. Absolutely. So, the Liouville, it's a one form on the cotangent bundle. So, therefore, it is a section of the cotangent bundle of the cotangent bundle. So, the cotangent bundle itself, you have to get something canonical, you have to go a little bit bigger. And it's worth trying to understand what it is. I don't want to be too formal, but I think it's very much worth trying to understand what it is. Thank you for this remark. It's a section of the cotangent bundle of the cotangent bundle. But here we're just talking about vector spaces, but still, we'll come very soon to the same thing for a cotangent bundle. So, this is just vector spaces. And now, what I'm going to define is you define omega. So maybe I'll even emphasize this which is standard and canonical, to be, there's a correctly normalized sign here. Look, you know, if you live long enough, which I'm lucky to have lived, and I hope to live longer, you spend many years trying to get the signs right. And this is the right sign. Okay? This is the right sign. D of a one form is a two form. Okay? And this is the canonical two form on this setup. Okay? That's it. Now, you're not very satisfied because you don't understand anything. So what I'm going to do is compute this two form and this one form in coordinates. Okay? I mean, you'll be much happier if you see this in coordinates. Okay, you ready? This is a test if I can do this. So there's perhaps a question here, whether I can do this or not. So the goal now is compute lambda and omega. I'll emphasize this, quite often I will call this the standard. It's canonical. I didn't have to have any additional information in coordinates. Okay.
Professor, I have
Yes.
one question. Could you explain what is mu P applies to T?
Let me get this up here now. Restate your question, please.
Yeah, what does this mean? What does this equation mean?
Okay, I'll go through it again. It's simple but confusing. Okay. P is a point. Okay, I don't know. Maybe this notation is bad. Maybe if you would prefer, I would say the one form at the point P evaluated on the tangent vector T. I don't know if was that the confusing point, perhaps.
But what is T, for example?
T is a tangent vector. What do you want from me? I evaluate a one form on a tangent vector. Right?
Okay.
Right? A one form is dual to a tangent vector. If you like, this is a covector evaluated on a tangent vector. But okay? No, this is great discussion. I mean, so please get aggressive with me and make me upset. Okay? Okay, so you evaluate, to define a one form, I have to tell you what it does on a tangent vector. Because it's a measuring device for tangent vectors. So I told you what it does. The crazy thing is that this point P is a point in the cotangent space, and therefore it itself is a functional, right? Yes? You see, the point P is V plus phi, but what that really means is it's the cotangent vector phi at the point V in this interpretation, right? And so I just apply it. I just apply it. That's it. It's canonical. It came to us from someplace far away. Okay.
Where is the field W? Where is it W in there?
Where is W? Yeah, W. So I had to tell you so the tangent vector I decomposed as this direction and this direction. W, of course, is something in the base. Now, generally speaking, that's what I emphasize. Generally speaking, I have no way to understand what is the horizontal component of a vector. So in reality, what I've done here, I cheated. I use it. I mean, I have the horizontal direction here. It's a direct sum. But for the simplicity, I chose this. But what I really did, I said I take this vector and I push it down here. And actually, what this thing is, it's a functional down there. So I apply it to every time. I start up there, go down there, and apply. But it's maybe more conceptual here because we do have this horizontal direction. To me, it's a very, very instructive example that I thought about to understand this for a very long time. I had to think about this. It's so simple, but I had to think about this for a very long time.
Does it have any real meaning?
Yes. You can ask Professor
everything is in the right position. I mean, it's a one form, and it's tangent bundle, and it applies correctly, but it seems very strange.
Very good. It's a very reasonable thing. For now, the reason I introduced this example is for you to understand the meaning of this form in symplectic geometry and Hamiltonian mechanics, and you will see that this is the fundamental form for that subject. Okay? I could, if you wish, introduce Hamiltonian equations in all sorts of mathematics from the 17th century, Newton, Leibniz, and so on. It's probably too early, but I mean, from Lagrange was rather early, and he understood this stuff. But he didn't understand the conceptual nature of what he was dealing with. What we're dealing with is this form. Okay? That's what I'm getting at. Just this form. And by the way, the key form at first for us will be omega. It will not be lambda, but lambda is in the background because, I mean, lambda is d if omega is minus d lambda. Okay? So in 10 minutes, I will have this form written in coordinates in physics letters. These letters will be called P and Q. Okay? So, one answer to your question is for future, in the future, omega will be dq dp. Whatever that means. So that appeals to you. Okay? And lambda will be, this is shorthand notation, by the way, used by Arnauld, which is a very good reference. So I mentioned again the name Arnauld. His book on mechanics is fantastic. And I would also recommend the book Symplectic Techniques in Physics by Guttleman and Sternberg. So these are two very, very good books. And this short notation I think is, and this is mine. So, and those are physics letters. And the letter Q means configuration variable, and the letter P means momentum. Quite often identified by a metric to velocity or something involving, we'll see, kinetic energy. So these are the letters that are important later on. All I want to say now is this stuff's canonical. Okay, here we go. So coordinates, so V has a basis. So a basis of V say, is E1 through En. And then we have a vector in V. You have coordinates V, x1 through xn. And this means that V is x1 E1 plus xn En. Okay. The dual basis, and this is just having fun. Dual basis here, I call f1 through fn. These are the functions. And then these coordinates will be y of, which will say y of phi, which are y1 through yn. And this means that phi, for example, is written in y1, f1, and yn. Sorry, this must be incredibly boring. So, the problem is we need to write basis of the tangent space. So, basis of the tangent space. So, the tangent space at V of V is ddx1 through ddxn. Right? And a basis of the cotangent of the tangent space.
But you never use that.
Huh? What?
You never have the tangent space at V. You have the cotangent.
Of course I do. The tangent space of W is in the tangent space of V.
Okay.
Yeah?
Yeah, okay.
W, I'm glad you said that. I'm very happy you mentioned it. I really did. Yeah? Okay. And the tangent space of maybe I'm writing too much now, but let's say the tangent space of V star phi is okay dx1 through dxn.
And so is dy1.
Hmm?
Isn't it dy1?
No, I want to. It is. I want dx. I want this. I think. So, no. You're absolutely, excuse me, that's nonsense. But there's so many identifications here. You're absolutely right. Yeah, thank you. Yeah, of course. Okay, so dy1. That's what you meant, right? Okay. Okay. So now I want to compute lambda. So lambda is a one form at that point. So lambda is a sum, say, of numbers, I don't care, a, I, dxi, it's a one form, plus, let's just keep it separate for a moment, bj, byj. So far I'm just writing notation, right? It's a one form, and so one form's written like this. Okay, now the first point is that the bj's are 0. Alright? Let's understand this. You see, the tangent space here, the vertical direction, the vertical tangent space, is here. See, the dual space is this fiber, right? So the tangent vectors to the vertical space are in this direction. So maybe if I write here this direction, you have the tangent vectors d, dy, j. Right? Vertically, in this direction. But this form doesn't care what's in the vertical direction, right? Because it only cares what the horizontal thing is. Actually, it's not even horizontal, it's downstairs, right? So that says they're all 0. So that means that then lambda is equal to ai dxi. And now I need to compute what ai is, right? Well, that's pretty trivial. So ai is lambda applied to d dxi. Right? And now lambda applied to d dxi is, as we know, phi applied to d dxi. Right? As a form. Phi is a point, but it's a form, really. So what is phi as a form? Phi is a form.
It's a function.
Huh?
It's a function.
It's a form. Well, it's a covector. It's a one form. Is it, yeah?
No, it's in V star. I think.
It's in. Absolutely. So absolutely. So phi. Now phi is at this point. So as you know, it's a form. So phi as a form. Now this is where you're going to argue with me. Is this form. So it's the coordinate of the point in a form. The coordinate's the y coordinate, right? I said the y coordinate's the form, the coordinate in the form direction, times its basis. Okay. Well, that means if you stick in here d here, you get delta ij. So this is just yj. Oh, I'm sorry, yi. Thank you.
But if you take phi to be that, phi has to be in the cotangent space of v. But
V, yes.
But
There it is.
But it's not in the. Isn't it in the dual space?
It's in the cotangent space. It's in the. It's a point. This is the point v phi. Really means phi as a cotangent vector at the point v. Right? Yeah. So I write phi as a cotangent vector at the point v. It's some linear combination of d dxi's. Well, the coordinates are y's. So it's this linear combination of that. You see, here it is as a point. Here it is as a point. That is a point in a vector space. But as a cotangent vector, it's really this. This is, in my opinion, the confusing point. I think you've struck a point. It's a point, it's a point there, in, you know, it's in a vector space.
Because you regard M as the cotangent.
That's right. You have to regard it that way. That's absolutely right. You have to stare at this for a while until you get tired, then you understand it. So, to make a long story short, lambda, let me write it here again, is where is it here? Is some yi dxi. Okay. So you'll be very happy to see that omega, I'll write the word standard again, is minus d lambda, so it is some dxi dyi. So this is an incredibly simple thing if you write it in coordinates, and it's absolutely canonical. It's there without any external information. Now the physics letters, the usual letters that I've learned from my friends are different. Is the y variables are called pi, and the x variables are called qi. So in the physics variables we have lambda is equal And now we have shorthand here. We don't write the sum and we don't write the i's. Quite often we just write p dq. And omega is dq dp. We just don't write the summation. And these things are canonical. I mean, this is a fundamental thing. You might just write down some coordinates or something. These are canonical. Nobody took, no further information. Okay? So you've seen these letters this way. Okay. Now, as an exercise, show, I'm going to assign you this, it's an easy exercise. Show that the canonical form, linear form, A, which I defined a long time ago in my lectures, A of VV prime is equal to V prime. V minus V prime is the same thing. Now this requires just a little bit of thinking. And it's the same thing you were talking about. On the one hand side, I've defined for you a two form on a vector space. And on the other hand side, I've defined for you an alternating bilinear form. Okay, so you have to make an interpretation. You see, there are two different things a priori, right? But it's really exactly the same thing. Okay? That's it. Well, that is perhaps something that I would guess that Lagrange understood very well in the early days of mathematics. Of course, maybe not in his formalism. And I don't know, maybe it was Liouville, so Liouville was interested in dynamical systems and many things. The turn of the century, in the 19th century, coming into the 20th century, this range. I'm guessing maybe he really did understand these things. Otherwise, this is rather new in mathematics, and it has really been a very strong positive influence on mathematics coming from classical mechanics. So, the general situation. I hope, yes?
Was it really Lagrange already, or it was only Hamilton who worked with P's and Q's?
According to my friends in France, Lagrange.
Because they're French.
Well, maybe I only read French articles, but
Lagrange is Italian.
Lagrange was from Piedmonte, so I am a very big Italian chauvinist, so you're probably right. Hamilton, although I did read that Hamilton perhaps was not the first person to understand the quaternions. It was some early French person, but Armand Borel told me that, so Borel was in Bourbaki, and he hated this lack of precision in French mathematics, but he told me French mathematics really needed Bourbaki, that nothing in French mathematics was right until after the Second World War. That all of this stuff was somehow very vague and very sloppy and so on. So I don't know what is really true here in the history of mathematics, but it's certainly true. Yes?
The second comment, I've just come back from a string conference in Munich.
Yes?
And the blackboard looked exactly like this one. We're using it today.
Good.
In research.
Good. Good.
So-called double tree theory works exactly like that.
Very good. I'm so happy because mathematicians are now joining up with physicists. They can talk to each other. Munich is an example where they're trying to have a nice concentration at the LMU or at the
It was an LMU conference, but it was at the Max Planck.
Oh yeah. So yeah, that's. I think you're maybe you are had to do with Professor West, but I don't know whether you were in Munich at the time or you have been in Munich or
6 years with West.
Oh yeah. So I knew he was. This was has very good coordinates. So the general situation is this. So here we go. Let Q, now a new word, a new letter. This is an n-dimensional manifold. And of course, without saying it, I think I almost always say that Q is connected. Sometimes we want to allow different components, but almost always connected. Okay, so Q will play, I'm going to draw here, the place here, this is Q. And we now consider the cotangent bundle of Q over Q. So this space here is the cotangent bundle of Q. And then I draw the same picture, the only picture I know in life. But maybe I make it a little bit better. I take a point here, let's say, I don't care, X, this is Q. And I take the fiber of the cotangent bundle over X. And now a little bit better letter after a point here is a covector phi at the point X. Right? I mean, that's what an element is here. Remember, I tried to convince you that V plus phi should be thought of as the covector, and that's where I translated it to, at the point V. And then I do the same stuff, and I'll even try to draw it in the same color. That we have the tangent vector here, T. Now I don't have a horizontal direction. There's no canonical horizontal direction. I have vertical direction, but no horizontal direction. So we can't do that. But we have phi. And what I have is I can say, well, I have T here, and this projection, maybe I call it pi. I can project this tangent vector down here with push forward. So this vector down here is the push forward of the tangent vector. Okay? And now I define the Liouville form. Liouville form. Okay, to be really, now look, this is a terrible notation. At the covector phi x, applied to the tangent vector t, is you apply the covector at x to the push forward of the tangent vector. That's what I did here, right? The point if there's a covector, you push the tangent. What does it mean a covector? It means something dual to the tangent space down here. I push it down, I evaluate. This is canonically defined. And omega, the standard symplectic, it's the standard form I have it sort of symplectic is minus d lambda. And in coordinates, now comes the key point. What are the good coordinates here? You have to be very careful. What are the canonical, and we say in this subject, canonical coordinates. So take coordinates q in the base. Right? Then you see a form at the point q, if you like, is equal to some linear combination of dq's, and this linear combination is this. It's some linear combination of so q is this is q at the of x here. This is some linear combination of these things, and this vector p is the coordinate of applied to phi. This is p of phi at the point. So this is the base coordinate, and this is the fiber coordinate. Okay. This is the base coordinate, this is the fiber coordinate. So the total coordinates in total, the coordinates are Q, P, written in this order, and they are Q1 through Qn, so it's 2 n-dimensional, of course, P1 through Pn. Okay? And if you check, lambda is equal to sum of Pi dqi, and omega is equal to sum dqi dpi. Okay. Any manifold and its cotangent bundle. Now you're starting to get a little bit happy about this. I mean, there's really, any manifold and its cotangent bundle gives you this form. So the appropriate word for this is the Q is called configuration space. And the cotangent bundle, or Q, is called phase space. Okay? Any manifold. Now what's going on here is the following. Where did this come from? Even probably from Newton. Earlier, I don't know. I know you like Gauss, but I mean, I can't give Gauss any credit for this. In high school mathematics, you do the following thing. I was very late in mathematics. I never did anything in high school except for geometry, and I'm very happy that I did. Because if you do geometry in high school, this means you contacted serious mathematics instead of just some monkey business of fooling around doing some calculation. In high school, you did the following. Somebody told you that you had this differential equation, right? You've seen it. Y'all solved this differential equation.
Much more advanced than what I learned in high school.
You were in China. This is probably, this is, was this post-Mao or pre-Mao? This is post, you're so young it's post-Mao. But everybody was trying to find a way to breathe this fresh air, right? So, anyway, you were probably some industrial area, a small town of size 30 million or something like that. I have a friend from France. We were giving a course together in Hangzhou. I told you I gave a course in Hangzhou, and he's from France. And we were looking around in Shanghai and so on, and the neighboring areas, and he computed out if you take some area around Shanghai and add up the number of people that live there, it's the same as in France. Anyway, this differential equation, I know this differential equation, right? Everybody here knows this differential equation, right? And you learn and you don't understand anything, that the trigonometric functions that solve this differential equation, you don't know what it means. But one thing people do that I never understood until I learned from my physics friends is they introduce a new variable which is called x dot. Right? X dot is a very funny thing when you just see this the first time, but you know, what? Okay. Well, I don't know. This is a very typical equation from nature. Second, because of Newton's various laws and so on, many differential equations are second-order differential equations like this, and you introduce y equals x dot, and you kill off the second-order thing and make it first-order, right? So it's, despite you being from China, you have to learn that the world is capitalistic. Chinese know this, even though politically they might debate. The world is capitalistic. So you say, this is a fantastic thing. Look at this thing here. It is x, that's y dot is x double dot, so this is y dot equals minus x. Right? That's the equation. On the other hand, you have another equation you forgot because you substitute. So the other equation is x dot equals y. Right? Okay. I don't like these variables. Why don't we say q dot equals p and p dot equals minus q. Why not? Okay. Why did I say q? Now the word configuration. This is the space variables. So when you see q, this means in the space variables. So the manifold where your whatever it is running around. You understand? It runs around. And it runs, by the way, it runs around and it overlaps itself and does all sorts of stuff in this manifold q. However, when you say, I go to this first, this is a second order differential equation. This is a first order differential equation. If you allow me to use these letters, which really have a meaning, you can make this precise, Q and P in position and momentum. Yes? This is a differential equation on the cotangent bundle of the real numbers. This is a function of one variable. This is a differential equation on the cotangent bundle of the real numbers. I'm sorry, that's R2, but it's the cotangent bundle of the real numbers. See it? Okay? So the second order physics equation of nature is lifted to a first order differential equation, an ordinary differential equation on the cotangent bundle. Okay? This is fundamental. When you look at it like this with the letters, it's very confusing. Right? I didn't understand when I first saw this, what in the devil does y equals x dot? I mean, it's incredible. I have some curve and I have x dot here. I mean, and suddenly y is a symbol. Yeah. But it's clear what it means. It's the induced differential equation on the cotangent bundle. Okay? So this is the introduction to the first Hamiltonian equation you will see. Please keep it in mind. And maybe now you're starting to get excited because it's on the cotangent bundle and there is a canonical object on this cotangent bundle, namely the symplectic, well, I call it symplectic form omega and the Liouville form lambda. So it's very exciting. Okay. Now, I think I will convince you even in this lecture how exciting it is. Okay. Definition. Symplectic manifold is a pair M omega, where M is a manifold, of course, where omega is a two-form on the manifold M, satisfying two fundamental equations, satisfying two fundamental things. One, it is closed. Okay, it is closed. And two, it is non-degenerate. Okay, I think closed I've discussed at great length what closed form means. It's d of it is 0. Okay, but let's emphasize what non-degenerate means. It means this. It means if you take the tangent space at any point P of the manifold and look at the orthogonal complement with respect to the form omega, it is trivial. I'm probably exaggerating my notation, but this notation will occur over and over again, so I want to have it. So it means the space of vectors which is orthogonal to everything. Right? Maybe I should write it out. The space of vectors, so the space of V in that tangent space, such that omega of V, so the contraction if you like, anything is 0. This is the space. The degeneracy is trivial. It's non-degenerate at every point. Okay, that's what it means. It's the best you can hope for. Otherwise, I could have the zero form. Right? I mean, incredibly degenerate. But we require non-degeneracy. So you can check easily that omega standard on the cotangent bundle of configuration space is a symplectic manifold. It is obvious that the form is closed. Well, let me just put under here d of omega standard. This is embarrassing. It is minus d of the Liouville form is 0. So it's obviously closed. And of course, if you wish, look at local coordinates. This form is about as non-degenerate as you can hope for. It is obviously non-degenerate. Okay. So it is an example of one of the first examples, one of the most important examples of a symplectic manifold. Cotangent bundle of any manifold, the phase space of any dynamical system of this type. Okay. Symplectic manifold. So I will make some remarks about things that are not symplectic manifolds, because there are other very simple properties that are easily violated. So it's like we talked about the Lorentzian case. Remember, I tried to convince you being a Lorentzian manifold is a serious condition. Riemannian manifold is not a serious condition. Every manifold is Riemannian essentially. So let me comment on some examples and some elementary properties. Let me just write here. It's clearly not degenerate. So let me have some remarks. Maybe remark 1. If M is symplectic, and M is compact, then the cohomology class of omega in the second de Rham cohomology is non-trivial. So it's the statement that that form is closed. That's part of the definition. It's a closed form. It's a statement. It is never exact. This closed form is not exact. That's the statement. It's a remember, this was the kernel of D from 2 forms to 3 forms. This form is closed automatically, so it's there, modulo the image from 1 forms to 2 forms. And the statement is that it is not exact, that it is not D of some form.
So what is W squared?
What
is the bracket W here?
The equivalence class. So, I'm sorry, so an element here is an equivalence class of a form. So you see, it's a vector space modulo another vector space. So in that, if you don't mind, I use that bracket notation to denote equivalence class. That's my notation, I don't know. It's not the lead bracket. There are many brackets, but this means equivalence for it, okay? Okay, now why is this? Watch this. Watch this very slowly. Okay. Suppose omega equals d alpha. Okay. Now do something completely insane. Let us look at the integral of omega dot 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 dot. So the n-fold dot product. So don't forget, omega is an n form, a 2 form. The manifold is necessarily 2n dimensional because it's a non-degenerate 2 form. Okay, when you've seen it here, I mean the p's and q's and so on, it's 2n dimensional. So I make an n-fold dot product here. So this is an n-fold dot product of omega. Okay? And now I write it here as n-fold dot product, wedge product. I said dach. The word in German is dach. It means the roof of a house. So it's a roof product in German. So n-fold dot product of this. This is this n-fold dot product of d alpha. Yeah, ha, 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 ha. A stupid calculation says this is d of this. It's a question of how d, this is Leibniz rule and how it works. You check what Leibniz rule means, it's d of that. And a non-stupid calculation is Stokes' theorem. The integral of d of a form, as I proved yesterday, almost in detail, the integral of d of something, this is terrible form. So let's call this tau for terrible. The integral of d tau over a manifold is equal to the integral of tau over the boundary of the manifold. Right? What's the boundary of a compact manifold? I can't find it. There's no boundary, right? 0. Well, that's great. So this is 0. On the other hand, non-degeneracy, if you check it, what it really means it's the same exact meaning to this n-fold wedge product. This n-fold wedge product being nowhere 0. This is an orientation form. This is nowhere 0. This is an orientation form. My integral was based on an orientation form. The integral of the orientation form is positive. The way the integration theory works. Everything was orientation preserved, remember? So it's positive. So this is non-zero. So this is nowhere 0. So this is another corollary. M is oriented with this form, has a canonical orientation. It's nowhere 0. On the other hand, that implies that this integral of all these things is positive. So it's a contradiction. So you see, yes?
Yes, I believe this, but what about that form, that omega? It is symplectic and it was minus d lambda.
Yeah, so?
Isn't it this exact?
Yeah.
And symplectic.
Okay, I'm very happy. This is good pedagogy. I'm very happy for this. What is the assumption here?
Symplectic. Im is compact.
Yes, and you see,
So
no matter what Q is, there's a very non-compact direction in the cotangent bundle, namely in the fiber of this bundle, and that's fundamental. No, it's very good. Okay? Very good. His remark is very good. Now let me tell you a little future, which I will prove using the technology of another wonderful mathematician named Jürgen Moser, is Darboux theorem states that in every symplectic manifold, given a point, you have PQ coordinates around it. You can find coordinates of type PQ always, but of course not for the whole manifold. So you can find that kind of coordinates exactly there for a big, usually a big open set in the symplectic manifold, but of course not for everything, if it's compact. Yes, the compactness is key here. And let me say this, in many applications, the manifolds are not compact, and therefore we, in order to handle non-compactness, we must impose conditions at infinity. There has to be some compactness in the problem. For example, in the cotangent bundle, some condition at infinity. So, thank you for this remark. Okay. Well, we have 10 minutes to have some fun at the end of this lecture. So before I get involved with formalities, let's have some fun. And I'm going to write down what I call the fundamental exact sequence of elementary symplectic geometry. But then afterwards, I won't talk about it in all detail, but I'll talk about one piece of it. So the fundamental exact sequence, which you must keep in mind at all times when dealing with this, is the following. We start with functions, which in the physics lingo are called observables. And there is a fundamental map, which I will at least temporarily call F, which associates to a function a field. To a function is associated a field, and this field will be of what I call local Hamiltonian type. I'm going to, this part of the, in the time allotted, this part I will explain. The kernel of this map is a very simple-minded thing, it's just the constant functions. And the co-kernel of this map is very interesting. You want to know how many of these beautiful vector fields you're going to get from functions, and the instruction to getting everything is the first Durand cohomology of the manifold. So this is the fundamental exact sequence. I will tell you everything about the sequence, and you should really keep this in mind. Okay? It's a summary of a lot of important information, whatever it is. So let me just talk about this map here. Let's talk about this today and have some fun with examples. Well, let H be a Hamiltonian. So these things are called Hamiltonians. So H is an observable. It's here a function. And the only thing I know how to do to a function is take d of it. Right? Everybody in this room knows how to take d of a function. Right? Now we think for a very long time. This symplectic form. Let me remind you what this is. Symplectic form has two entries that you can do on the internet, and you see we can have fun within that. You know how it is. At the end of a sentence, it's absurd. You put this little thing. And my wife always tells me I don't do it right. So if I do, my wife, she doesn't look at all my emails, but she checks whether I do this. So, okay. What you put in here is a vector, right? And what you put in here is a vector. If you put a vector in here and let this other thing run, it is a functional on vectors, right? And since this form is non-degenerate, every functional is obtained in this way. Well, I hope you will not object if I then say there is a canonically defined form, vector field. There's a canonically defined vector field that is obtained from a function by the pairing omega, which means if you put this thing in the first argument, let me put it in there, you get a one form, and this one form is dH. Okay? That is the mapping I temporarily called F, script F. It associates to a function a field. And you can see what goes to 0 is just the functions that are killed by D, and so this is this. So I've really explained the first part of this thing. Okay? Now, maybe we have 5 minutes. Yes, we do. Let's have some fun. Okay. So, example. Let us go to the cotangent bundle of something. I don't know. Let us go to the cotangent bundle of Rn. Okay? So Q equals Rn. We go to the cotangent bundle of Rn of Q with the standard symplectic form. Cotangent bundle of Rn has global coordinates, global canonical coordinates, QP. Okay. Now comes some deep thinking if you understand physics, and I don't understand very much, but one of the first Hamiltonians you should think about, H, should be, well, we might write it as Q squared plus P squared, or something like this. Let's emphasize what that means. It means this. Let's emphasize there are only n of these. Okay? You've seen these, right? But Professor Schub in his course, he does it. Okay? So this is what I've got to believe this is one of the first Hamiltonians you would think about writing. This has something to do with harmonic oscillators. Right? So let's see what the deal is. Let's compute the Hamiltonian equation for the harmonic oscillator. Okay? The harmonic, what does it mean, the Hamiltonian equations? The Hamiltonian equations means you integrate the vector field associated to the Hamiltonian. Right? The vector field, H goes to XH, that is an ODE, that's a vector field, and you solve that ODE, which means you find the one parameter group of solutions. Right? So let's find it. Well, everybody knows, I guess. The trouble with me is I don't even know the stuff, because if I change signs, and suddenly instead of the sine and cosine, I have hyperbolic sine and hyperbolic cosine. And the phenomena are completely different, as you know. Right? So, anyway, I get confused here, whatever is going on. Okay, let's go. So DH, physics number. You know, so physics, I told you, copy every notation. Physics people really know to write numbers and write everything, so just copy. So, okay, DH, well, it's very nice because this is some QI dQi plus some PI dPi. Okay? That's DH, right?
Where's alpha?
Alpha.
Oh, it's 2.
Huh?
Sorry, I thought it was alpha.
What did you say? You said something. So finally it's Germany, but there's humor in the room. What is going on?
I thought you put h equal to q squared plus p squared over alpha.
Oh,
It's 2.
very good. Yes. I'm sorry. Yeah. Very good. You know, these Chinese guys, symbols, you know, in the language really play a huge role. If I do something incredibly complicated like that, you would say, oh my God, what is this guy doing? Does it mean something? I did this one time in Pakistan, and actually what I wrote there almost meant something, and it was very dangerous. So, okay, so now what's the job? What's the job? The job is this. Our omega is dq dp. Everything's separated here. That makes life easy, so we really only have to do things one at a time. So the vector field I have to put in here to get the one form. Now let's see what I want to get the q thing. Let's get the p thing first. So what I want to do, the vector field xh, the p thing is easy because I put something in here to kill the q thing, and p thing is left over with. So I know, having done that I certainly, this is that part of the calculation. You understand what I'm saying? If I put this in here, right, this q kills this and gives me the p, and this stays over with, and that's that. P dp. And now I want to put something in here to give me this, but in order to do that I want to have q left over. So I obviously have to put it in here to kill it, but I have to bring it forward to kill it, so I have to have a minus sign. So this is sum q minus q dp. Okay. Okay. Well, that's the vector field. And now you know what the ODE is. The ODE is, yeah, if you have an ODE, it is Q point equals the coefficient of Q. Here's what's going on with Q. Q point is P. Ha ha ha. And then P point, is whatever is going on with P here, is minus Q. Right? Well, I was lucky. Okay? That says that if you take this quadratic Hamiltonian, and many, many Hamiltonians in life are quadratic. I think it's fair to say that many Hamiltonians are quadratic. You take this quadratic Hamiltonian in linear space, you're dealing with this differential equation. Okay? It says this is a Hamiltonian equation in this sense, and it comes from this map, which associates functions to vector fields. Okay? We will talk about that in the next time we meet.